today we're going to talk about two graphs that you're going to see a lot of. The first graph is a position versus time graph, and you did this in the lab we did earlier this week. You were creating position versus time graphs. The thing to know about a position time graph is that the slope tells you the velocity of the object. This is super, super important. Slope equals velocity. Now, what I don't want you to do is memorize that. I don't want you to like make a flashcard that says position time graph slope is what, and you're just like velocity, like the way you would pull it out of your brain for like a vocabulary word or something. What I want you to do is be able to figure out, because this is not the only graph you're going to have. In a few minutes, I'm going to talk about velocity time graphs, and the slope on that graph is something different. And then there'll be more graphs between now and May where you need to be able to interpret what the slope is telling you. So do not memorize what the slope is for each graph. I want you to be able to figure it out. So how would you figure out what the slope is telling you? Well, what's the definition for slope? Rise over run. So let's look at the first part of this graph, this first straight line right here, from point O up to point A. What is the rise? And I know it's 4. I don't mean numerically. What is the rise a measure of? So this rise right here. So the y-axis, I should mention, students earlier today were confused a little bit because the y-axis is measured in x with units of meter. What do we mean by x? Position. X is the position. Like x on the y-axis, I'm confused. So x is the position measured in meters. So what would this rise be? The rise is the change in x, the change of position, which is the displacement. Now what's the run? The run is the change in the time. What is displacement over time? Velocity. So this is equal to velocity. Or a simpler way to do it is just analyze the units. Look, so slope is rise over run. What's the unit for the rise? The rise is measured in meters. What's the unit for the run? Seconds. So you can very quickly figure out what the slope is telling you. Slope is velocity. Now, the next thing I want to do is let's look at the 3 segments of the graph. So the first segment is from the origin up to point A. How would you describe that motion for this circle here, for point O up to point A? Yo. Constant velocity. The velocity is constant. Now, how would you figure that out? Well, look, if slope is velocity, well, what do we notice about the slope of this first line segment? The slope is constant. If the slope is constant, the velocity is constant. Now, guys, I want you to triple box and highlight what I'm about to say, because this is huge. Whenever you come across the words, like we just said, whenever you come across the word constant velocity, that is synonymous with something else. What is constant velocity? Zero acceleration. This is very, very important. Constant velocity is the same as zero acceleration. And if you think about it, it's true. So look, I'm going to demonstrate for you. I am moving with constant velocity. Right? Not going faster, not going slower. If I move with constant velocity, what's my acceleration? 0. Okay. All right, the next line segment here. So constant velocity, A equals 0. Okay, the next segment, from A to B. What's going on from A to B? How would you describe this motion? It's at rest. The velocity is equal to 0, right? How do I know the velocity is equal to 0? Well, what's the slope of this line from A to B? 0. If the slope is 0, the velocity is 0. Or another way to think about it is, look, like just imagine the object. So let's say it's like a person walking or something. What is happening from A to B? The object is staying at the 4-meter position. The object is not moving. It's staying at the position that's labeled 4 meters. There is no motion from point A to point B. So the velocity is 0, which is also a constant velocity. And if the velocity is constant, the acceleration is 0. So we have a constant 0 velocity. Now, from B up to C, what's going on there? It's accelerating. The velocity is increasing. So the thing you're going to be doing is you're going to be looking at what happens to the slope. What happens to the slope as we leave point B and we start heading up this curved segment? What's happening to the slope as we go up that line segment there? The slope is increasing. If the slope is increasing, the velocity must be increasing. So this is increasing velocity. Okay? So is there an acceleration? Yeah? Would you call this a positive acceleration or a negative acceleration? It's a positive acceleration. And by the way, what would a negative acceleration look like? A negative acceleration, so here we have position, time, so say you go from at rest. So what we had here was a positive acceleration. What would a negative acceleration look like? It would go like that, where the slope is changing, but it's becoming more negative, more negative, more negative, more negative, right? That would be a negative acceleration. Okay? All right, so I got a couple questions. Any questions on this? So to sum it all up, the slope is velocity. You should know that constant velocity is synonymous with 0 acceleration. So I got 3 questions for you. So I'll give you a couple minutes to look at these. Okay, so find the average velocity from point O to point C, then find the instantaneous velocity at t equals 2, which is right here, and then find the instantaneous velocity at t equals 9, which is right there. Now, real quickly, yesterday I talked about the difference between average and instantaneous. If you're driving your car and you look at your speedometer, what type of velocity is that? Instantaneous. Well, actually, I should use the word speed because there's no direction given. Instantaneous is how fast you're moving at a specific moment, whereas average is between 2 points. And look, do those 2 points have to be far apart in time, or could they be close together in time to calculate an average? They could be close. Like an example, yesterday we talked about the acceleration of gravity. If I take this calculator right here, assuming no air resistance, so what's the starting velocity of this calculator? 0. When I let it go, how fast will it be moving after 1 second? Using gravity as 10. 10 meters per second, right? Because the acceleration of gravity we learned yesterday is 10 meters per second squared, which means every second an object experiencing the acceleration of gravity, every second the velocity of that object will change by 10 meters per second. So look, 0 velocity, and then at t equals 1, it's going at 10 meters per second. What's the average between 0 and 10? 5. So the average velocity for that first 1 second of fall would be 5 meters per second. Does that make sense? My whole point is this. When you're doing an average, it doesn't have to be like a big time interval between the 2 points. The time interval could even be like half a second. A lot can happen in a half a second, okay? But simply put, instantaneous is at a specific moment. Average is between 2 moments, which could be close together. Got it? All right, so take a couple minutes and answer these 3 questions. The average velocity from point O to point C. Let's use the definition for average velocity. Velocity is displacement over time. So we're focusing on point O up to point C. Okay? Remember, displacement only cares about starting position and ending position. So you're really not concerned with what happens in between the 2 points. Displacement cares about starting point, ending point, and the distance in between. So what is the delta x from O up to C? So this is at 0 meters, that's at 10 meters, so what's the change of position? 10 meters. Okay, what is the time interval from point O over to point C? 12. So this gives us 10 over 12. In physics, we round this to the nearest tenths place. We're not concerned with sig figs in physics. We'll just round that off to tenths place. So it's approximately 0.8 meter per second positive. Positive indicates the direction. Okay? Now, the thing I want you to realize here, all we did here is we basically connected point O and point C with a straight line and took the slope of that line. You take the 2 points you're focusing on, connect them with the straight line, take the slope of that straight line, that will give you the average velocity between those 2 points. Okay? All right, next question. Find the instantaneous velocity at t equals 2. So let me revert this. Back up. So we want this question here. So finding the instantaneous velocity at t equals 2, that's right here. Now, the thing that's really nice about this question, can anybody tell me what the nice thing is about this question? As opposed to the next question, which is find the instantaneous velocity at t equals 9. What's nice about this point compared to this point? Yo.
This is constant velocity.
So t equals 2, this falls on a region of the graph that's a nice straight line where the velocity is constant. So look, guys, I want everybody to realize this. The instantaneous velocity at 2 seconds and at 3 seconds, 3 seconds would be right about there. Will the instantaneous velocity at those 2 points be the same or different? It's the same. How about at t equals 1? Same. Because look, for this whole first region, the velocity stays the same. So really, to answer this question, what do we have to do? We need to figure out the slope of this line right there. So I'm going to use point O and point A. I'll use this point and this point. Those are 2 nice points. So velocity, delta x over delta t. Using point O and point A, the rise is 4, the run is 4, so this gives 1 meter per second. So that's the instantaneous velocity at every point from 0 to 4 seconds, because it's constant velocity from 0 to 4. Okay, next question. Find the instantaneous velocity at t equals 9. So t equals 9 is right here. Now the thing that makes this a little more tricky, if you look at this part of the graph, is that a straight line? Nope, it's on a curve. So how would you go about finding instantaneous velocity at a point on a curve? So you might think, oh, Spaldo, this is calculus, which you'll be doing this in calculus class, but you actually don't even need calculus to do this. This physics course is non-calculus based. So what would the calculus way be? The calculus way would be to find the derivative. Find the derivative at t equals 9. Derivative is a fancy name for slope. Derivative is just a calculus way of saying slope. Okay? So here's the non-calculus way of doing it. The non-calculus way, if you want the velocity at this point, what you do is you draw a tangent line, which is already done for us, right? Would everybody agree that this line right here is tangent to the graph at t equals 9? You draw a tangent line at t equals 9, and then take the slope of that tangent line. All right, so I'm going to go this point and this point. I'm going to use those 2 points to take the slope. So the rise is about 5. That's going to be 5 meters over 7. So that comes out as about 0.7. Right? Okay, any questions on position time graphs? So now let's look at velocity versus time. All right, velocity versus time. There are 2 things that are important. And again, don't memorize these 2 things. Like, don't stick these on flashcards and just cram them into your brain. The thing you want to do is understand what's going on here. So let's first talk about slope. So just like we did before, think about what slope is. Slope is rise over run. So I'm going to pick out 2 points on a straight line here. So I'm going to pick these 2 points right here. So if we took the slope of this line, what would the rise be? So over here on the y-axis, we have velocity. This rise is the change of velocity. What's the run? The change of time. So we get change of velocity over change of time. What's that?
Acceleration.
That's acceleration. Okay, so the slope tells us acceleration. Or like I said before, you could just get in the habit of analyzing the units. If you just look at the units, the rise is measured in meters per second. The run is measured in seconds. That gives us meter per second squared, which is acceleration. Okay? Okay, the other thing you have to know is what the area under the graph tells us. So I'm going to pick out an easy part of the graph. So let's say like from there to there. No, actually, sorry. Let's go from 15 to 20. So from 15 right there to 20 right there. When you calculate the area under that segment, how do you do it? Area for this situation would be what? Base times height. Now let's look at what happens here. What is the base for this region? 5 seconds. What's the height for this region? 8 meters per second. What do you notice? The seconds cancel out, and we're left with meters, which is displacement. Right? It's the same logic. Like, look, you make $8 an hour, and you work for 5 hours. How much money would you make? $8 an hour for 5 hours. 40 bucks is the exact same thing. 8 meters per second for 5 seconds, right? Now look, what if you're on a part of the graph that is a non-constant velocity? Like let's say you were focusing on this other part in here. If you're focusing on this part in here, how would you go about finding that area? So here, let me clean this up. So let's say instead, what if we were focusing in here? You would go area equals what? 1/2 base times height. Now why do you have to include the 1/2? Well, I know it's a triangle, but like why does it make sense that you have to have a 1/2 there? Because look, what's the velocity right here? At this point right here, what's the velocity? 0. What's the velocity up here? 8. Is this thing moving at 8 meters per second the whole time? What's the average of 0 and 8? 4, which is why the 1/2 is what we need. Basically, the 1/2 gives us the average velocity, right? So include the 1/2. If it's a triangle, you got to have the 1/2 there. Okay? All right, final thing, but I'm going to give you some questions to answer, but final thing I want to point out here. Notice that these numbers here are positive. These numbers here are negative. What is plus and minus in physics? Direction. So I want you to imagine that this graph pertains to a car. So here's the car. To the right is plus, to the left is minus. When the graph begins, which way is this object, which way is the car moving when the graph begins down here? To the left. The motion starts out to the left in the negative direction, okay? Now, what would the area here be? The area down here, is this going to be plus or minus? Minus, because the velocity is minus. The area up here is going to be plus, because the velocity is plus. What has to be true about the journey of this car? The starting point and the ending point must be the same point. The starting point and the ending point must be the same point. And the reason I know that is because the negative displacement and the positive displacement are the same. Right? So look, I'm going to act this out for you. I'm going to act this out for you. So this way is negative, right? To the left is negative. So what does the object start by doing? Moving at a constant negative velocity, and then what happens at t equals 5? It begins to slow down, slower, 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 and then what happens at t equals 10? Stops, then what? It starts coming back in the positive direction, right? And then it reaches a constant velocity at 15 seconds, moves at a constant velocity, and then we don't know what happens after t equals 20, right? But basically what happens is this object moves to the left for 10 seconds, it stops, and then starts to move in the positive direction, and it must return to the starting point because the negative area is equal to the positive area. Okay? All right, 3 questions and then we're done. Oh man, talk about perfect timing. All right, you know what? I'm going to answer these because the bell's about to ring. So first question, wants the average acceleration from t equals 0 to t equals 20. So what you're going to do, you're going to connect those 2 points with a straight line and take the slope, right? So what's the change in velocity from here to there? 16. How much time did that take? 20 seconds. So it's 0.8 meters per second squared. Positive. All right, instantaneous acceleration at t equals 10, right here. How do we find the instantaneous acceleration? That's just going to be what? The slope of this line right there. So you can use any 2 points you want. So I will use this point and this point up there. So acceleration, the rise there was 8. The run is 5. So this comes out as 1.6 meter per second squared, positive. And then the last question is 0 meters. The reason it's 0 is because the negative displacement and the positive displacement are the same, which means there's no overall displacement.